Jet Performance, presented by Ursula Triplet, Embry-Riddle Aeronautical University. I'm going to be touching on a few topics today: angle of climb, vector addition, unit circle resource, rate of climb, absolute ceiling, and then, of course, the references. The angle of climb. When an aircraft takes off, the angle from its flight path and the ground is known as the angle of climb. As you can see in this illustration that I've made, you can see the direction of the ground, okay, and then you can see two airplanes, and we're going to say that they're moving at the same speed, and they're taking off. One is in no wind, and the other is taking off against a headwind. And you can see the one that has no wind, its angle of climb is right here, and then the second one, you can see because it's taking off into the wind, and let's say that they're moving at the same amount of knots, you can see it has a steeper angle of climb. And this is actually useful to be taking off into the wind if you're trying to avoid obstacles such as trees that may be in your path. So the book has a lot of information about the angle of climb. They have it. They know that we all know that thrust and drag are two forces that act along a flight path. Lift acts 90 degrees to the flight path and the weight acts towards the center of the earth. The weight vector is replaced by two other vectors. One is perpendicular to the flight path, which is represented as weight cosine y, and y is just gamma. And then one is parallel to the flight path, weight sine gamma, and realistically acts at the aircraft's center of gravity. Aircraft has to overcome its drag and its weight. And I've linked arrows here. As you can see in the textbook illustration, right here, you're going to have this right triangle. And we all know that a right triangle has a corner of 90 degrees. For steady velocity, the forces along the flight path must be balanced, and as we see, thrust must now balance with the addition of the weight for a given climb angle plus the total drag. Thus, thrust minus drag minus weight sine gamma equals 0. So they have that rewritten as sine gamma equals thrust minus drag divided by weight, which can equal just thrust available minus thrust required divided by weight. Okay, and then we can see the increase in thrust has a decrease in drag, and you can see this from the diagram here out of the book. A maximum climb angle will occur at the point where the maximum thrust is at an excess. So you have thrust available minus thrust required at its max, and the sine value increases as the climb angle increases. I wanted to touch on vector addition. I know it wasn't a topic expressed for this week's assignment. However, I do think it's important to understand this aspect in order to understand the other areas that we're looking at. So vector addition, the course text gives us an example of an aircraft flying east at 300 knots with a north wind of 30 knots. Okay, and so they're giving us, I'm going to explain to you where they got this equation from. So they got it. So the Pythagorean theorem is just a statement that says a squared plus b squared equals c squared. So we know this to be true. It's proven to be true. We accept it as true. So they're expressing it as v rotation squared equals velocity angle of climb squared plus velocity of weight, of wind speed squared. I believe that's what that is. So they're doing ground speed equals, so how did they get the 301.5 knots? Well, I'm going to tell you. Okay, so they take the 300 knots and they put it in here and they square it, right? So we know that that is the direction it's flying and how fast it's flying. So we put that in there and we square it, and then we get the 30. We could take the 30 knots and we do that for the 30 knots. And we also do the same thing, we square it. So 300 squared is 90,000, right? Follow me? And then 30 squared is 900. So you have 90,900. Well, how did they get, so they didn't tell you how they got the 3015 knots. They just show you they took the square root of it. Okay, so how did they do that? Why did they do that? Because in the equation, they didn't show you that that VR here on the side actually still had the square on it. And when you take the square root of this, you have to take the square root of the other side. So now they're down to the VR, and now you have 90,900 square root, which is 301.49, and they rounded it up to 301.5. And that's where that came from. So that's where the 301.5 knots comes from. Pretty easy to follow so far, right? Okay, now don't lose me here. All right, we're looking at a right triangle. The tangent of an angle is the length of the opposite side divided by the length of the adjacent side. And that's expressed as tangent x. X is just a variable, and it's going to be replaced with a number at some point. On the opposite side divided by the adjacent side. Okay, so we have the triangle. We know it's a 90 degree. It's a polygon, right? Polygon is means three sides. Okay, we know it's 90 degrees. They told us in the book that 301.5 knots was the hypotenuse. Now, what's a hypotenuse? Okay, it's the direct opposite side of the 90 degree angle, right? It's the longest side opposite a 90 degree angle is the hypotenuse. Okay, and we all know that a triangle has to equal 180 degrees on the inside. So you have your 90 degree angle, and then you have two acute angles. So I'm just using this as an example here just to show you where they got these numbers from. So in the book, it tells you the drift angle is the angle whose tangent is weight divided by the angle of climb equals 30. So they have 30 divided by 300 equals 0.1. So which is 5.7 degrees to the right south of the aircraft heading. Okay, so where did they get that 5.7 degrees from, right? That probably doesn't make sense to you where they got it from. So I'm going to tell you. So you need to convert from radians to degrees using 180 divided by pi. So how do we do that? So we take 180 divided by pi, and then we times it by the tangent of 0.1. And that gives us 5.748 degrees, right? So now we're in degrees. We're in a unit of measure of degrees. So I'm going to go ahead and, which is 5.8 to the right south of the aircraft heading. So they have 5.7 because they only went out to the 10th, but I went out to the 1000th mark. And it probably could be argued either way, whether to round up or down. So I'm going to go with 5.8 on that one. All right, and then we're going to move along. And you can see here, hopefully you followed along pretty well and it makes sense. If you're unclear, let me know. So now I'm going to go ahead and show you. I got a resource slide coming up for you. The unit circle. This is really important to understand if you're trying to do calculus equations. It's very helpful. Yes, yay calculus, said no one ever. So the unit circle has 4 quadrants. So the top right quadrant of this circle, and everybody knows a circle is 360 degrees, correct? Okay, so the top right here is quadrant 1. And this unit circle is read from the 0 degree mark here on the right, and it goes from right to left all the way down back to the 0 degree mark, which on the bottom side is 360 degrees. So you have to do quadrant 1 is top right, quadrant 2 is top left, quadrant 3 bottom left, quadrant 4 bottom right. We're going to be staying in quadrant 1, top right. And everything in this quadrant, all signs are positive. There are no negative signs here. And this is important because I'm going to be showing you where some of these numbers came from in the book. And then you're going to go, so easy. So now I'm going to be talking about the rate of climb. The rate of climb through vector resolution in figure 1.7 to resolve the vector v subscript a over c into a component v over h, which is the horizontal, parallel to the horizontal, which will represent the ground speed, and a vertical component v over v, subscript v, which will represent the rate of climb. We simply draw a straight line vertically upward from the horizontal to the tip of the arrow, v subscript a divided by c. This vertical line represents the rate of climb, and the horizontal line represents the ground speed of the aircraft. What does this mean? What is this nonsense? We don't need that. Well, you do need that. I don't know why they make it so complicated. The rate of climb. Okay, so 1 knot unit of conversion is 101.269 feet per minute. That is just 1 knot equals that many feet per minute. That's the conversion rate. So the course text gives an example of an aircraft steadily climbing at 200 knots. This same aircraft makes a 30-degree angle with the horizontal. Okay, so what do you do with that? Where did they get these numbers from? Well, I'm going to tell you. So they have the horizontal equals the angle of climb cosine 30 degrees. So they put the 200 here, but where did this 0.866 come from? Oh my, where did they get that from? So this is where the unit circle comes in handy. So we go back to the unit circle, right? And we find in top right quadrant 1, 30 degrees. We go up here and we find, now why is it a cosine? Why? Because it's on the x-axis. So we all know that an axis has an x and y axis. So here you have two numbers. But how do I know which one to put in? So this one on the left is always going to be your x variable. On the right, it's going to be your y variable. So you've got to have the square root of 3 divided by 2, and that is equal to 0.866 if you did a calculation. So they just put the decimal value in place of square root 3 divided by 2. And that, so they have 200 times 0.866, and we'll go back to the slide here. And that's why they call it a cosine here. So they have 200 times 0.866, which does equal 173.2 knots. That's the ground speed. So make sense so far? Okay, now we're going to go down to this other section. And I'm using these equations out of the book because you may have read them. There's a little bit of grasping at that you sort of get what's going on. So I thought I'd just use them to solidify your understanding of what's being discussed. So we have here v subscript v, v subscript a, c again. Sine 30 degrees. So where do they get this 0.5 from? Right? What is that? So again, go back to our resource table. We find the unit circle. We find the 30 degrees. And now we're finding the y variable, which would be the 1/2, which in decimal would be 0.5. And I believe it doesn't matter if you put the zeros in like they have it in the book. You're going to get the same answer. 0.500 is how they have it, but you can just do it with 0.5. It'll still work the same. So coming back to this, now we have sine 30 degrees. So we have the 200 steadily climbing. So we have the angle of climb rate of 200 times 0.5. We got that from our unit circle. 30 degrees sine is 1/2. So we times 200 times 0.5, which equals 100 knots. Okay, so how do we figure out the feet per minute for the rate of climb? Well, now we take the knots, and you saw up here that I have 1 knot equals 101.269. And you times it by your knots. So we times that together, and we actually get 10,126.9 feet per minute. So that's the actual answer that should have been in the book. I mean, if they were good around to a whole number, I would have done 10,127. I don't know if the 3.1 feet per minute makes a difference, but That's where that number came from. They probably just rounded it up to a whole number to make it easier for you to try to understand. Okay, again, rate of climb. 1 knot equals 101.269 feet per minute. So in the book, they have this equation 6.6 that we've all seen. Rate of climb equals the velocity of knots, sine gamma in knots, which is equal to the velocity of knots times the thrust available minus the thrust required divided by the weight, and that's knots. And then you have the 101.3 velocity of knots times the velocity of knots times the thrust available divided by the thrust required divided by the weight, which equals the feet per minute. So where did the 101.3 come from? Why is that in there? Where'd that come from? Well, that comes from that 1 knot equals 101.269, and they rounded it up to 101.3. So that's why they have it in here, because you're taking knots and they want it in feet per minute. So you're converting the knots to feet per minute, and that's why they're timesing this equation by the 101.3. So they have here that the velocity for maximum rate of climb cannot be determined by a simple examination of the thrust available minus the thrust required curves. So when they say that in equation 6.6, that it shows that the rate of climb depends on velocity and excess thrust, both of which are variables. However, by selecting various airspeeds and finding the corresponding values of thrust available and thrust required from figure 6.13, then solving equation 6.6, a plot of the rate of climb versus velocity can be made similar to figure 6.20, and the velocity for maximum rate of climb can be found. Whoa, that's a lot of information. So the rate of climb is the altitude gained with respect to time. That's the simplest way that I could probably explain it. And referring to my diagram below that I've made to illustrate this point, both aircraft will reach the same altitude at the same time. So this is just given that both aircraft here, I'm going to say that they're traveling at 80 knots. Both of them, the same speed. One of the aircraft is traveling at 80 knots into a 20-knot headwind, giving it a takeoff speed of 60 knots, right? So why is it 60 knots? Because we're both traveling, both airplanes are traveling at 80 knots. One has no wind resistance, so it takes off at an airspeed of 80 knots. But 20-knot wind, the airplane going into that, is being pushed back, so you'd have to minus the 20 knots off of the 80, so it takes off as if it's at 60 knots. So you can see here that the angle of climb is much steeper with the one traveling into the wind. And like I said earlier, that it's useful when you're trying to avoid obstacles such as trees. So here I have the rate of climb. You can see I have the X and the Y axis. And here, if the aircraft reach an altitude, this is just a figure I've put in to help you understand. If these aircraft reach an altitude of 10,000 feet in 5 minutes, then the aircraft are climbing at 2,000 feet per minute. Because what do we know? We know that the rate of climb is the altitude gained with respect to time. So if both of these aircraft are traveling at the same speed, with respect to their angles of climb, doesn't matter that one's steeper, it's still the same. So they both reach 10,000 feet in 5 minutes. We take 10,000 feet divided by 5, you get 2,000 feet per minute. Okay? Now I'm going to talk about absolute ceiling. As altitude increases, climb performance decreases. The climb rate at the absolute ceiling altitude will be 0 feet per minute. Why is that? Well, as you go up in the sky, the air particles get thinner, and there's just no more room for lift. They're just too far spaced apart. They're sparsely there. They're not going to give you any more lift. No matter how much you try or want to go higher, it won't work. So if the thrust available equals thrust required, the aircraft can still fly, however, can no longer accelerate or climb. So on the diagram from the course text, it shows a T-38 with a thrust required minimum of 830 pounds. So if the thrust available equals the thrust required of 830 pounds, then the aircraft will be at its absolute ceiling at approximately 90% RPM sea level. So I've marked that here. So it just means that you can't go any higher. That's your absolute ceiling.